everyone, I'm Dr. Rizwana, working as a Professor of Physics in Institute of Aeronautical Engineering. So today I'm going to discuss some definitions related to quantum mechanics. So coming to quantum mechanics, in all my previous videos, I have discussed about wave-particle duality of radiation, and then very important concept related to quantum mechanics, that is de Broglie hypothesis. Then we have derived expression for de Broglie wavelength in terms of different parameters. And then we have discussed what exactly are matter waves. And by discussing their properties, we have come to conclusion that matter waves are not electromagnetic waves, but there are some new kind of waves. And also, in order, of course, this de Broglie, he has given this hypothesis theoretically. So, in order to prove it experimentally, then we have taken this experimental Davison and Germer's electron diffraction experiment. This experiment it gave first proof for existence of matter waves. There we have taken material particle electron and we have accelerated it by applying potential. And then in the end, we have seen that it is exhibiting as a wave. And then once we have these matter waves which are material particles in motion exhibiting wave nature, we have derived wave equation, that is Schrodinger's time independent wave equation. And then this wave equation of matter wave, it has got one very important solution given in terms of wave function psi. And we have discussed in detail what is the significance of this wave function. And we have discussed about Born interpretation of wave function. Then after that, in quantum mechanics, we have in the end discussed about a particle enclosed in a potential box. And this particular concept, it has led to very important conclusion of discrete energy levels that has given to quantization of energy, and of course the name quantum mechanics. So we have seen that if we take a free particle and if we bond it in a potential well, okay, we have enclosed it in a potential box, then we have observed that its energy, it is going to be dependent on width of the box. And also as taken by classical physics, where we talk about having continuous energy levels, this quantum mechanics, it has given conclusion about quantization of energy, that is having discrete energy levels. And because of this, we are able to explain certain phenomena at atomic dimension, which was not done by classical physics. So all these concepts we have already discussed. Now today, by taking into consideration all these topics, we are going to discuss some of the definitions related to this module. So moving further, coming to first definition, as you can see on the screen, what is quantum mechanics? So just now I am talking about quantum mechanics. So as you can see here, quantum mechanics, it's a theoretical science which deals with atomic dimension, that is nothing but which deals with the study of motion of microscopic objects. So when we talk about microscopic objects, we are talking about material particles. So when we take a dimension of very small sizes, when we are talking about their behavior or when we are trying to study their motion, then that particular theoretical science is nothing but quantum mechanics. So what is quantum mechanics? It's a theoretical science that deals with the study of motion of microscopic objects that have both observable wave-like as well as particle-like properties. So mainly it focuses on dual nature of matter waves. Then coming to next question, state Heisenberg's uncertainty principle. So what is Heisenberg's uncertainty principle? According to this principle, it is impossible to specify precisely and simultaneously the values of both members of particular pairs of physical variables that are associated with the atomic system. So here in this case, to be more precise, I have taken that particular pair as position and momentum, and we have defined this uncertainty principle as it is impossible to know both the exact position and exact momentum of an object at the same time. Then next, related to quantum mechanics, we have Planck's law. So state Planck's law. So we know that what is Planck's law? Planck's law, it is related to spectrum of black body radiation. So it talks about energy spectrum that is irradiated from a black body. So here black body, it is acting as a good emitter. So according to Planck's law, we have energy being radiated in the form of discrete packets of energy, and those packets of energy are nothing but photons. Now, what exactly is a black body? Planck, he spoke about black body and he has explained behavior of light radiation by taking into consideration black body. And what is a black body? We know that black body, it is a perfect absorber as well as perfect emitter. So what do you mean by perfect absorber? Which absorbs radiations of all wavelengths incident on it, and it is also a good emitter, which is going to emit all radiations of different wavelengths and frequencies. Now, when it will act as good absorber and when it will act as good emitter, because it cannot exhibit both the properties at the same time. So you will observe that it acts as good emitter when we take it to high temperatures, and it is a good absorber at very low temperatures or when we go for normal temperatures. And as temperature increases, emission power of a black body, it is going to increase. So that such type of system, it is called as a black body. And here we can also make or construct a black body. For that, what we'll do, we'll make one halo shaped enclosure, and we are going to paint inner surface of that enclosure with lamp black. And this particular enclosure or cavity, it will have one hole, and shape of the hole is maintained in such a way that when light radiation enters the enclosure, then inside the enclosure it will suffer multiple reflections and it will stay inside the enclosure only. It won't come out of the enclosure. So we are able to make such black body. So man-made black body is also possible, but it may not to that 100% approximation, but at least we can make it to 99.99% approximation. Then coming to next definition, define photoelectric effect. Now coming to this black body or photoelectric effect, these are the main phenomena, okay, that were explained completely based on quantum mechanics, or we can say that they have paved the path for the origin of quantum mechanics. So coming to definition of photoelectric effect, we know that here in photoelectric effect we have two terms. So one is photo, other one is electric. So if we take certain metals, so when we go for metallic elements like sodium, lithium, and if we expose the surface of that metal to very high frequency light radiation, then we'll observe that from the surface of the metal surface, there will be emission of electrons, and these electrons, they are going to give rise to electric current. So photoelectric, you can say that here, incident energy which we are giving is light radiation, optical energy, and output power we are getting is our current. So that emission of electrons from a metal surface when we expose it to high frequency radiation is nothing but photoelectric effect, and this phenomena, it was given by scientist Einstein. And here when we take this photoelectric effect, here we talk about interaction of light radiation with matter in the form of small corpuscles or particles known as photons. Here collision is taking place between two particles. One is photon of light radiation and second one is electron of metal surface. This is very important conclusion that have been taken from photoelectric effect. Then related to photoelectric effect, we have one more definition, recall stopping potential. So what is stopping potential? So in this case, as we know that there is emission of electrons from a metal surface when we expose it to high frequency radiation. So potential difference in order to just stop the photoelectric current is known as the stopping potential. So how much potential we need in order to stop, and it is at the initial stage where we are going to just stop the photoelectric current, that particular potential, it is known as stopping potential. Then moving further, again related to photoelectric effect, we have one more term, explain the meaning of work function of metal. So what do you mean by work function? So here, as you can see on the screen, the minimum amount of energy required in overcoming the binding energy of constituents of the metal. So what do you mean by binding energy of constituents of the metal? Here we are talking about breaking of the bonds, and also from the metal electrons, they are coming out, they are gaining energy. So once they gain energy, what we have? We have ejection of electron from the surface of metal. So that minimum amount of energy which is required in order to make electron just come out from the surface of a metal surface, it is known as work function of a metal. Okay, then next is our one more phenomena, and related to that phenomena we have Compton wavelength. So what is Compton wavelength? So Compton wavelength, it is for a particle and it is defined as wavelength of a photon whose energy is same as mass of the particle. So what is Compton wavelength of a particle? It is equal to wavelength of a photon, and in this case photon energy, it should be equal to mass of the particle. Then we have Compton effect. Define Compton effect. So just like photoelectric effect, here also there is interaction of light radiation with matter. So in this case, what we are going to do, when we are going to focus high frequency radiation like X-rays on certain scatterers, then what we'll observe here is out of those scattered radiations, we are going to have two types of radiations. One is modified radiation, another one is unmodified radiation. So what is unmodified radiation? Where whatever scattered radiation is there, it has got same frequency and energy as that of incident radiation. Whereas in case of modified radiation, the energy and frequency it is going to be less than the incident radiation. And again, this Compton effect, when we take and when we consider what is the basic logic behind this Compton effect, here also interaction is taking place between photon of light radiation and electron of scatterer. And because of this interaction, whenever high energetic photon give its energy to electron, then obviously out of scattered radiation, we are going to get radiation which has got low energy compared to incident radiation. And then coming to next definition is what are matter waves. So this comes from our de Broglie's hypothesis. So we know about wave particle duality exhibited by radiation. So as according to de Broglie's, like everything is symmetric in nature. If light radiation can have both dual characteristics, having like where it has both wave properties as well as particle properties. Similarly, de Broglie, he said that if you take a particle, and especially he's talking about material particles. So if we take material particles like electrons, protons or neutrons, and if we make them move, then that moving material particle, it will exhibit properties of a wave, and that wave it is called as matter wave. So what are matter waves? Waves associated with moving material particle, they are called as matter waves. And what is one more name given to matter wave? They are also called as de Broglie waves. Then next, proceeding further, we have recall phase velocity. So what is phase velocity? As you can see on the screen, it is defined as velocity with which each individual wave travels. So here we are talking, as you can see, the next term, group velocity. So what is group velocity? When you consider many number of waves traveling in a medium, then the velocity which and all those group of waves together, region in which we have superposition of many number of waves, and these waves, they are differing in their wavelengths. That particular superposition of waves having different wavelengths, it is called as wave packet. And we'll say that all these waves will be going with one common velocity which is called as group velocity. But in that wave packet, if I consider velocity of each individual wave, then that particular velocity, it is called as phase velocity. So here we have discussed about group velocity and phase velocity. So first of all, we should know about wave packet in order to understand these two definitions. So what is a wave packet? Where we have superposition of so many number of waves traveling with different wavelengths. So those group of waves, they are called as wave packet, and overall this wave packet, it will be moving with one common velocity which is called as group velocity. And whereas if I consider different waves inside the wave packet, each wave it will be moving with one particular velocity, and that velocity is nothing but phase velocity. Then next one, very important concept, or we can say very important conclusion drawn from quantum mechanics, that is nothing but quantization of energy. So what do you mean by quantization of energy? As I was discussing earlier also, when we take classical mechanics talks about continuous energy levels, and here classical mechanics, it can explain motion of like huge bodies or celestial bodies. But when it comes to atomic dimension, and when we take this concept of continuous energy levels, then many phenomena are unexplained. So that's why we have taken quantum mechanics, where we talk about quantization of energy. What do you mean by quantization of energy? Where we say that energy is not continuous, but it is discontinuous. What do you mean by discontinuous? These energy levels are well separated from each other, and only certain particular values of energies are allowed. Those are called as discrete energy levels, and having such discrete energy levels or discrete energy packets is nothing but quantization of energy. And we know, according to Planck's, those discrete energy levels, they are called as photons. Then next, related to wave, we have one very important law called as Bragg's law. So what is the statement of Bragg's law? We know that Bragg's law, it is for diffraction, and of course diffraction, it is exhibited by a wave, but this particular Bragg's law, it is used to show existence of matter wave. As I was talking about experimental proof for existence of matter wave, that is nothing but Davison and Germer's experiment. In that experiment, we have used this Bragg's law in order to prove that when we make an electron move, it is behaving as a wave. So what is the statement of Bragg's law? According to Bragg's law, when we expose a crystal, to X-rays, then when these X-rays go inside the crystal, when they fall on different crystal planes, then let us suppose that their angle of incidence is theta. Then from each and every plane, these X-rays, they are going to get scattered. And let us suppose that angle of incidence and angle of scattering or angle of diffraction, if it is same, then what we will observe here is, if path difference between those scattered radiation, if it is integral multiple of wavelength, then constructive interference takes place and you will have formation of bright spot on the screen. And that is nothing but Bragg's law. We can say Bragg's law of maxima. So we'll get maximum intensity only if those reflected rays from different planes of the crystal, if they are maintaining path difference, which is integral multiple of wavelength. Then moving further, we have, what is the meaning of normalization of wave function? So we know what is a wave function. Wave function, of course, associated with matter waves, directly it has no direct physical meaning. We know that it's not measurable, it is not an observable quantity. So these are usually complex. So in order to explain such complex functions, Max Born, scientist Max Born, he has come with one particular interpretation. And according to that interpretation, when we have such complex wave functions, we have to multiply them with their complex conjugate. And when we multiply them with their complex conjugate, we get mod psi square. And what is mod psi square? According to this Born interpretation, it represents probability density. And based on that probability density, normalization condition, it can be defined as the probability of finding the particle in entire space. So here we are talking about entire space. If it is equal to unity, and wave function, if it satisfies that condition where probability of finding the particle is 1, then such wave functions, they are called as normalization function. Then next, we are talking about potential box, and here we need to explain what is the behavior of particle in one-dimensional potential box. And if you take what is a particle in one-dimensional box, it is nothing but fundamental quantum mechanical approximation describing the translation motion of a single particle which is confined inside infinitely deep well from which it cannot escape. So here, what we have done in order to construct a potential box, we have taken a free particle, and then at two regions we have applied boundaries in such a way that particle is enclosed between those two boundaries and it cannot come out of those boundaries. So that is the concept of particle confined in a potential box. And such particle, it is called as bound particle, and related to this bound particle we have a free particle. So coming to next definition is, define a free particle. So obviously, what is a free particle? Which has no constraints and which can move anywhere freely, and actually we'll say that its potential energy is constant, but we'll take that potential energy to be 0, and all energies are allowed for such free electron. There is no limitation for the energy associated with such free particle. Then what is degeneracy? See, here we know that when we talk about discrete energy levels, we know that for one particular value of n, that is nothing but quantum number, we are going to have one particular value of energy. But what you will observe here is, for same value of n, you may have like degeneracy is having different values. If you take different quantum states, so here I am talking about different values of n, and for different values of n you are going to have same value of energy. Suppose if we talk about n is equal to 1, if I take quantum number value to be 1, then corresponding to n is equal to 1, we are going to have only one energy even. But here, what is degeneracy? Degeneracy is when we take different values of quantum numbers. For these different values of quantum numbers, we are going to get same value of energy. So that particular state, it is called as degeneracy. Then next, of course, quantum wavelength, where we talk about shifting wavelength corresponding to the scattering angle of 90 degrees is nothing but quantum wavelength. And then next, wave function. What is wave function? Which is associated with matter waves. As we know that this wave function, it defines the displacement of wave. And also, if you take this wave function, it is dependent on position coordinates x, y, z. And also, it is dependent on time t. So, based on this wave function, we have two types of wave equations for matter waves. One is time dependent, another one is time independent. In time independent, we'll make our wave function just function of coordinates x, y, z. And whereas in time dependent, we'll take into consideration factor time. And of course, as I told, according to Max Born, what is this wave function? If we multiply this wave function with its complex conjugate, then we have probability density, that is probability of finding particle at a point, at a particular point in space. Then coming to next one, next definition, define eigenvalue and eigenfunction. So eigenvalue is nothing but energy of a particle which has got one particular value of energy, and the wave function for that particular quantum number. Suppose if I take n to be 1, then corresponding energy value it is called as eigenvalue, and corresponding wave function value it is called as eigenfunction. Then next, what are the applications of Schrodinger's wave equation? So coming to Schrodinger's wave equation, of course, it will help us to find the electrons in a metal, and also it will help us to understand what is the behavior of particle that is enclosed in a potential well. It helps us to find what are the energy levels taken by an electron when it is bounded in a potential well. So it helps us to understand difference between energy levels associated with free electron as well as bound electron. Then next, we have this Bohr model of atomic structure. So according to Bohr model, we know that inside the atom, we have electrons, protons and neutrons. And if we consider electron in an atom, it revolves around the nucleus in orbits. And these orbits, they are stationary states. And we know that this electron, it is going to be in that particular orbit unless and until we supply energy. When we supply energy, it will come out of its orbit and it will take part in conduction. So that is nothing but absorbing energy and jumping to high energy level. Then next, now we have taken Bohr model, but what exactly is quantum mechanical model of atomic structure? So according to quantum mechanical model of atomic structure, so this of course it was taken by considering Schrodinger's and Heisenberg's theory. And when we have taken classical mechanics, we are able to explain only motion of certain macroscopic bodies. But coming to this quantum mechanical model, it helps us to apply to very microscopic particles like electron, protons and neutrons. And it will take into consideration wave-particle dualism. So here we talk about wave-particle dualism and also probable distribution of electrons instead of orbits. So here we'll more focus on particle, that is electron. But whereas our Bohr model, it focuses on orbits in which electron is moving. And the next question, how does quantum mechanics is going to differ from classical mechanics? Now, if you take classical mechanics, as I have discussed before, it applies to only macroscopic properties or properties of very huge bodies. Whereas, when you take quantum mechanics, it can be applied to microscopic particles and mainly talks about probability of finding the particle in space. And then there is what is Schrodinger's wave formulation of quantum mechanics, and according to this, this particular formulation, it allows a quantum system to view as a wave. So as you know that if you have a particle, then we are associating wave with such particle, and this was given by Schrodinger's wave formulation of quantum mechanics. And here, because of this evaluation of wave, we are able to describe about a system with respect to time. And then next question, how is quantum mechanics used in everyday life? So here we have many like applications, day-to-day applications. As you can see here, we have quantum theory applied to lasers. It is applied to CDs, DVDs, solar cell and fiber optics. So all these particular which we are using in everyday life, they can be like explained based on quantum mechanics. Then coming to next question, why is quantum mechanics difficult? Now, coming to classical mechanics, it is simply saying that bodies, they move with continuous energy levels. It's a simple concept of explaining. But coming to quantum mechanics, when we talk about discrete energy levels, so we find quantum mechanics to be difficult, and also because we are taking into consideration atomic dimensions. So to consider quantum mechanics to be difficult, why? Because here systems which follow this quantum behavior, they don't follow one certain particular rule, and they are going to, here of course here we are talking about degeneracy, where we are saying that there may be different energy states, okay, and having same energy, there is nothing but we are talking about degeneracy. And even what you are observing here is, here when we talk about existing of several different states at same time, and even there will be change depending on whether they are observed or not. The next, who invented quantum mechanics? Of course, it was who are the two founding fathers of quantum mechanics? First, of course, Niels Bohr, and then we have our Max Planck. Then what is quantum effect? So according to quantum effect, the particle itself is behaving as a wave. So that particular concept is nothing but quantum effect. And then we have what is the value of Planck's constant. Planck's constant value, it is given as 6.6 into 10 power of minus 34 joule second. Then next we have what are quantum numbers. So we know that there are many quantum numbers, and what is the use of these quantum numbers? So there are certain set of numbers which are used to describe the position and energy of an electron in an atom. And coming to different types of quantum numbers, we have principal quantum number, orbital quantum number, which is also called as azimuthal quantum number, then magnetic and spin quantum numbers. Then next, who proposed principal quantum number? So this notion or notation of energy levels for particular atom, first it was given by Bohr, and then after that Schrodinger equation, he has evolved this concept of two-dimensional Bohr model to a three-dimensional model. So what he has done, whatever two-dimensional model was proposed by Bohr, it was extended to three-dimensional by Schrodinger's. And what does this particular principal quantum number represent? We know that of course this principal quantum number, it takes values from 1, 2, 3 and so on, and they represent energies associated with electrons. And here, why there are only 8 electrons in outer shell? Now we know that of course when we say that there are 8 electrons in outermost orbit, then it has attained its octet configuration. So why we say that there are only 8 electrons? Because the stability of an atom, there is 8 electrons. It derives from stability of noble gases, and these are the elder term of inert gases, also known as unreactive or noble gases. Then of course, how do we find the principal quantum number? And we know that this particular value, it is the level of central electronic shell. All orbitals at same n value or at same key stage, and of course depending upon all orbitals on the second main stage have the principal like this. They generally, what does this n represent? First, when we are talking, it talks about size of the orbit. So if we take n to be 1, then we are talking about innermost electronic shell, that is nothing but orbit. N is equal to 2, next orbit, then n is equal to 3, next orbit. So the path in which or orbitals in which electrons are moving, they are given by these different values of principal quantum number. Then next, what is quantum energy? And here, of course, quantum. When we talk about quantum, we talk about charge, angular momentum, and discrete energy levels in terms of photons. And when we say quantum energy, we are talking about discrete packets of energy known as photons. And these photons are very much part of electromagnetic radiations like X-rays, gamma rays. And here, these quantized energy packets, they talk about wave-particle dualism also. Then coming to next question, what do we mean by spin of an electron? So we know that if we take atomic model, in that atomic model we know inside we have nucleus, and this nucleus, it contains protons and neutrons, and around this nucleus we have electrons moving in different orbits. So when this electron is moving around the orbit, it spins about its own axis. And that spin, it won't be a complete rotation, but what it will do, halfway it will go for clockwise, and then it will come back, and then halfway it go for anti-clockwise. That's why when we give values for the spin, we'll take it as plus half or minus half. So what is our spin? So if the we can say that if the electron spins on its clockwise, it is known as spin up, and whereas if it goes in counterclockwise or anti-clockwise, then we take it to be spin down. The next, what is ML? So what does ML represent in set of quantum numbers? So ML, it is called as magnetic quantum number, where we talk about orientation of orbital, and that orientation, it can be talked in terms of energy, which is given by principal quantum number n, and also it is given in terms of shape of orbit, which is given by L. So that is nothing but where we talk about orientation of orbitals. So when we consider orientation of orbitals, suppose if you take a p orbital. So if we take p orbital, then we'll say that there are three different ways of orientation of orbitals. And what are those three different ways? Px, py and pz. Similarly, if you go for d orbital, then there are 5 different ways. So that different orientation of orbitals, it is given by this magnetic quantum number. The next, of course, spin quantum number. So when we apply magnetic field or electric field to an atom, then here we talk about change in the spin or orientation of spin of an electron. It is given by this spin quantum number. And of course, as I said, it can have plus half value or minus half value depending upon its orientation. Then coming to last definition related to quantum mechanics. Here, how we can describe properties of an electron which has got these 4 quantum numbers N, L, Ml and Ms. So if you take here, if you take an electron, each quantum number associated with electron, it can be explained in its own way. So that explanation, it can be in terms, as we take N is principal quantum number, which will define the size of the orbit or energy associated with the electron. Then azimuthal, it talks about shape of the orbit. Then magnetic spin quantum number, where we talk about orientation of orbitals. And spin quantum number, where we talk about spinning with respect to magnetic field. So, and its direction, positive or negative, depends upon direction of its spin. So, these are the different definitions related to quantum mechanics. So, I hope you are able to get more information about quantum mechanics, or you are able to learn more about quantum mechanics from all these definitions discussed today in this video. So, I am going to stop my video here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.